Hi everybody. This is take two. The first time I clicked close instead of save, so I'm doing this again. Um, it feels like a really long time since I've seen any of you. I think it's been a little over a week. It feels like it's been months. I'm ready for school to start normal again. I don't like this online learning thing. It's much more work and um all of this is taking a lot of time, so I'm gonna get right down to it. Um, the last thing we did before I sent you, well, not before I sent you off, before the end of the world happened, was we spoke about drift velocity, how quickly the charges in a circuit move through the circuit, and um, how it depends on the resistance or conductivity of the material and how many charges there are per volume and so on. Um, we did a couple examples. I'm going to post some solutions from the textbook, and I'm going to post the section numbers in the textbook for you to review that. We're not going to spend any more time on it. It is a fairly small topic, and there's not much to do with it. The what we're going to talk about this time is resistors. Basically, this lesson is going to cover everything we need to know about circuits with just batteries or power supplies and resistors themselves. So we'll talk about what happens when you have resistors in parallel, in series, when you have complex circuits where you can't really break it down into just parallel and series. And we're going to talk about Kirchhoff's rules, which many of you might have heard of the rules, one or both of them. We'll go over them. We'll go over some increasingly complicated examples of them. Um, and You're going to have a homework assignment that's a combination of problems from Albert as well as the textbook. Albert doesn't really have enough questions about really complex circuits, so the questions there are a little bit more basic. I apologize for the increased number of questions I've given. Most of the questions on Albert shouldn't take particularly long. They're not a lot of work. The questions from the textbook are the more involved ones. Okay, so we're going to dive right in. I'm going to very quickly go over basically what you learned last year. I'm not going to derive anything. I'm just going to lay it out there. It's all in the reference table. Um, but I will. This lesson is going to focus on how do we use Kirchhoff's rules um, to analyze complex circuits. We're going to start with the basics. So we're going to move right along. And we're going to start by talking about Ohm's Law. Ohm's law is the empirical relationship that the potential difference or change in electric potential is equal to the current running through the element of a circuit times the resistance of that element of our circuit. So we represent a resistor with the little squiggly line, and the the potential difference is really the change in potential from one point to another. So if we label these 2 points A and B, and their value of electric potential as VA and VB, the change in electric potential, which is also called the voltage, which we're usually going to drop the delta sign just because it becomes cumbersome. This change in electric potential from A to B is equal to the potential at B minus the potential at A. Again, a delta sign is a change. Changes, we always do final minus initial. So if I want the electric potential from B to A, I subtract VA from VB. Because I'm going from VA to VB. If I want to go the other way around, I'll get a negative result. this is because, VA or VB might have a higher potential than the other. And so if I go one way, I increase. And if I go the other way, I decrease my electric potential. But really, remember, voltage is a difference in electric potential between 2 points. Now let's move on and let's talk a little bit about electric power. So we're talking about the power dissipated in a resistor or other element of our circuit. So the power dissipated by a resistor is equal to the amount of work over time, which is equal to, in the case of charges being moved around, it's going to be equal to Q times the change in potential divided by the time. And Q over T is just a fancy way of describing the electric current running through our circuit element or resistor. And this is equal to I times V, current times voltage. This is something you've seen before. Now, voltage is equal to I times R, making use of Ohm's Law. And so we can rewrite power as I squared times R. We can also write I, using Ohm's Law, as V over R. And this lets us rewrite power a third way as V squared over R. Each of these methods of writing power is, they're equivalent. They all mean the same thing. They'll all always get you to the same place. But sometimes one of these three is more useful than another. It's just more appropriate to the particular circumstance that you're dealing with. For example, let's say you have a circuit where the voltage across everything is held constant, and you change out a resistor. Well, this formulation is going to be really easy to determine what's going on with the power, because if voltage is held constant across everything, then if you increase resistance, power goes down. Decrease resistance, power goes up. Similar for the others. So it's just a matter of picking the one that will get you to what you're looking for the fastest. Oftentimes, what you want to avoid is sometimes you make a change. For example, maybe you increase the voltage, and as a consequence of doing that, for example, maybe you increase the resistance of your circuit, and as a result, current goes down, right? It's not immediately obvious what will happen here. Maybe the current will win because it's squared, and so the power will go down. In fact, that is what happens. But it's just a little bit easier to see that using one of the other equations where something is being held fixed. So now let's move on to what happens when we have resistors connected to each other in different ways. So we'll start with series. So when you have resistors connected in series, what it means is that the current entering at one place has to leave all of it through a single point on the other side. So for example, in this case, all of the electric current that passes through the first resistor has nowhere to go but through the second resistor. And as long as we're talking about steady state circuits, the rate at which current has to pass through at the left side here has to be the same as the rate on the right side, because whatever current goes in here in a certain amount of time has to leave here in the same amount of time in order for this to be a steady state circuit. So one way of thinking about the definition of two things being connected in series with each other is that they are on a single branch, there's a single path through them, or that the current is held fixed through the two of them, or more than two of them. When we have resistors connected like this, they basically just make a bigger resistor, right? Resistors are lengths of material that impede the flow of current, and so if I have two resistors end to end, it's like one bigger resistor. And so the equivalent resistance is simply the sum of all the resistors added in series. So let's take a look at this circuit. All three of these resistors are connected to each other in series with each other, right? Because whatever current is pushed out of this end of the battery, it's a single connected path from one to the other. Note that this end of this resistor is not directly connected to any of the other resistors. This end of the resistor is only connected to this first end. So they're not in parallel. One leads directly to the next in a line, in series. That's what the word series literally means. So in this case, we could write the equivalent resistance of our entire circuit as R1 plus R2 plus R3. And since we know the total voltage of our circuit, which is just V, we can compute, for example, the total current, which would be I is equal to V over the equivalent resistance. So now we know the current through all of them. Now, since they're in series, the current is forced to be the same. And so we see that the current is the same through each of these resistors. But if we use Ohm's law, we see that since each resistor has the same current, but potentially a different value of resistance, the voltage across each of them will be different, right? And so we can compute the voltage for each individual resistor as VI is equal to the current through the resistor as a whole or through the branch of that circuit times the value of that particular resistor. And I'm not going to do all the math again. You should have seen this before. But since we know that the potential difference from here to here is just the voltage of the battery, we know that because it doesn't really matter which path you take. If I go from here from here across my battery, I've gone up a potential difference of V. If I go all the way around, I went up from here to there, V. When I go all the way around, I have to end up at whatever the value of potential was that I started, which means all the potential that I gained from, that I gained from here to here was used up, or I shouldn't say used up, was lost once I completed this circuit. It's not really lost, it's simply that it changed, because the value of V, the value of potential, depends on where you are. And so along a wire, there's no resistance, and so by V equals IR, there's no change in V. But then every time I go through a resistor, the value of my electric potential changes. In particular, as long as you go in the direction of the conventional current, the potential decreases across a resistor. And then it goes through wire again, nothing happens, it decreases again. It goes through more wire, it decreases again to its original value. It's important to note that I haven't used any up. You don't use up potential. Potential simply changes depending on where you are. Just like the potential created by a point charge, for example, depends on where you are. So now let's talk about when we have resistors connected in parallel with each other. Now, in parallel, we see that this end of resistor 1 is connected directly to this end of resistor 2 through nothing but wire. So there's no change in V along this wire because there's no resistance. V is IR. So if R is 0, then delta V is 0. And likewise, there is no difference between the potential here and here because, again, these 2 points are connected by nothing but wire. So the change in V from here to here is nothing. And so if these 2 points are at the same value of V, and these 2 points are at the same value of V, then the difference from here to here is the same as the difference from there to there. In fact, we can more easily say, we can just call this point A, and we can call this point B. And once again, since there's no difference, there's no change in V along just bare wire, since R is 0, the value of potential between all these three, at all these 3 points is the same on this side, and so the potential difference from A to B is whatever it is, and it's the same for each branch of our parallel circuit. And this gives us, let me label this, R1 and R2. If you go through the derivation, you can see in the textbook, or you can look in your notes from last year, but when we have resistors connected to each other in parallel with each other, then 1 over the equivalent resistance is equal to the sum of 1 over the individual resistances. For another way of writing it is the equivalent resistance is equal to 1 over R1 plus 1 over R2 plus so on for each of them. And if you just so happen to have two resistors, it is convenient to note that the equivalent resistance for two resistors simplifies to R1 times R2 over R1 plus R2. It's, I don't know, an arithmetic mean, or I don't know. I think it has a fancy name, but I never remember what these things are. So this is how we can compute the equivalent resistance of branches of circuits with parallel elements. So let's take a look at this circuit. And here, it should be clear, again, that each of these resistors is connected in parallel with not only each other, but with this battery over here, right? So this end of the battery, the negative terminal, is connected directly through nothing but bare wire, which means no change in V, from here to here to here to here. So all of the right sides of these resistors are held at the same value of potential, whatever value the negative terminal of our battery is at. Usually we just call that 0. Here, our positive terminal, if it's a 12-volt battery, we might call this 12 volts. It's connected directly by nothing but wire to all the left-hand sides of these circuits. If you can hear that rolling sound, sorry, that's my cat. He's going crazy. You'll just have to deal with it. And so since the left sides are all at whatever value of V the left side of the battery is, and the right sides are all at whatever value of V that the negative terminal of the battery is at, then the delta V across each one of these resistors is going to be the same. And so since the potential difference across each resistor is the same, and in this case identical to the potential difference across the battery, then we get, using Ohm's law, delta V equals I times R. And what that tells us is that each resistor draws a certain amount of current, and it's independent of any of the other resistors, right? Because this has a certain value of V. It's set just by the battery. It's not affected by the presence of these. For example, if I were to cut off this part of the circuit, it wouldn't change what's going on with R1. R1 is getting this much potential one way or the other, and so it's going to draw that much more current. And so each one of these draws current independently of the others. That is going to result in a greater value of total current through the circuit. Every time I add a new resistor, it's going to draw its own current independent of the others. This is related to the fact that if you look at the expression for the equivalent resistance over here, right, the more resistors you add, the bigger the denominator becomes, which means the smaller the equivalent resistance becomes. So when I add resistors in parallel, I actually decrease the overall resistance of my circuit. One way you can think about that by analogy is, well, resistors impede the flow of current. One of the ways they do that is by restricting sort of the path of the electrons. They're forced to squeeze through something that impedes their flow. But if I add an additional root up here, I'm not further impeding the path of these electrons. In fact, I'm doing the opposite. Instead of the electrons having to squeeze through the existing paths, I'm giving them a whole other path. So think of this like a crowded room trying to leave through 3 doors. If I open a third door, it's not going to make it's still going to speed up how quickly they're able to exit. I'm going to have a greater flow of people outside of leaving the room than if I only had 3 doors open. So that's kind of what's going on in a simple parallel circuit. So now let's talk about combination circuits. Combinations are when we have resistors connected through both series and parallel combinations. So in this case, we can actually see that things are a little bit more complicated. Let me label these. So if this is R1, R2, and R3, it should be clear that R2 and R3 are in parallel with each other, right? Using the same analysis that we just used over here, we can clearly see that R2 and R3 are in parallel with each other. R1 is not in parallel with R2 or R3. R1 is also not in series with R2 or R3 because the current that flows through R1 actually can split between R2 and R3. There's not one unique path for it to travel. So this is a little bit more complicated. We've already talked about this with capacitors, so the most straightforward way to do this is to simplify our circuits using equivalent resistance. And while it's true that R1 is not in series with either R2 or R3, R1 is in series with this entire branch, right? So if I take this whole branch here and I replace it with a single resistance, R23, the equivalent resistance of this branch, then this branch, this whole section is in series with R1 because whatever current goes through R1, whatever current leaves R1, while it will split right here, in the end, it all does still have to leave this section. So there's going to be some fuzzy business going on inside of here, but as a whole, R1 is in series with this entire piece of our circuit. So the easiest way to analyze it is compute the equivalent resistance, rewrite it as a simple series circuit, and now you can do all the analysis you want. If you find, for example, the voltage across this section of the circuit, let's do an example. If I connect this whole thing to a battery, then I know that V equals I times the equivalent resistance, which is equal to I times R1 plus R23. Then I can find the total current if I want, for example. The total current is simply equal to V over R1 plus R23. Now I also know that this total current is I can use this to calculate the potential difference across each part of this circuit. So for example, I know that the current I is the same through here and through here. And so I know that the voltage across R1 is simply equal to I times R1. So I can plug this I into there. I also know that the voltage across section 2,3 is equal to I times the combined resistance of 2 and 3. But this is also equal to V2 and V3 because the potential difference across R2 is the same as across R3, which is the same as across this whole section. They share that resistance in common. So we can use this to then, once we have the voltage here, we can calculate the current through each individual resistor because the voltage of 2 is equal to the current through 2 times the resistance of 2. And since I just calculated the value of this voltage and I know the value of the resistance, I can find I. And so one way that you may have learned in the past how to deal with these kinds of combinations is to make a V, I, R, and sometimes P table, where you can add up all of these for example, resistance 1, resistance 2, resistance 3, and the equivalent resistance, or the equivalent part of the circuit. And so each one of these gives you a table. This is really nice because we know that V is equal to IR. So if I find V, if I know R1, R2, and R3, that's not an R, then I can calculate the equivalent resistance, and since I know the total voltage, I can find the total current, and since I know the total current through the circuit is the same as the total current through here, I can do that. Then I can do this analysis over here to work out the values of V2, V2, and V3. And once I know V2 and V3, I can calculate I2 and I3, and I also have I and R1 here, so I can calculate V1. And now I know everything, and if I want to, I can fill in the powers over here by whichever equation I want. So a VIR chart or a VERP chart is really handy to just keep track of everything. It helps you keep track of what you're looking for, what you still need, what you've already found. And sometimes it can be helpful in your chart to include, for example, parallel elements. So if I add R23 here, I know that the current here is the same as the total current of our circuit. And so this is how we found V23, which is how we found V2 and V3 here, because they're the same. One nice thing about this, if you don't have these equivalent sections of your circuit, or if you do and you're careful about what you're doing, if you add up V1, V2, and V3, it should be equal to the total voltage. If they're in parallel, if they're in series, I'm sorry. So if you keep track of what's in parallel, what's in series with what, when you add up all the different elements of your circuit, you should find that things match. For example, I2 and I3 together should add up to give us our total current, because all of the current had to split here into these two branches. So I2 and I3 together have to give us back our total current. So this is just a handy way of keeping track and organizing yourself. Now, unfortunately, a VERP chart is not always as helpful when you have a more complicated circuit. So this is an example of like a simple combination circuit. But what if we have more complicated examples? What if we have an example like this one? Take a look at this circuit for a little bit and try to identify what parts are parallel, what parts are series. See if you can make it, if you can redraw it to be a little bit simpler. I'd pause the video right now, take your time, think about it, and when you're ready, you can start the video again. So hopefully what you found is that you can't do anything, right? R1 is clearly not in series with either R2 or R3, right? There's a junction, there's a split right here. So whatever current is going through R1 is not guaranteed to also be going through R2 and R3. There's not just a single path to take. It's also not in parallel with them, because the right end of this resistor, it is connected directly to this end, but this end is not connected directly to this end. There's a battery in between them. Likewise, for R2, there's a battery between these sides, there's a battery between these sides. So these are not all in series. In fact, R2 and R3 are not in series with each other. They're not in parallel with each other. This end of the R2 is connected to this end of R3 through nothing but wire, but there's a battery between the other two ends. So the potential difference across here won't be the same as the potential difference across here. So for this kind of circuit, we can't actually really use a VIR chart to very good effect, because I can't break the circuit down into manageable bits. I kind of have to just deal with the whole thing. And so the way that we do this is we use what we call Kirchhoff's rules, or I think technically his name is pronounced Kirchhoff or something, but we're American, so we're going to butcher his name. And in particular, we don't actually use his name all that often when referring to them. We call the two rules the Junction Rule and the Loop Rule. The The junction rule is the more straightforward of the two. What it says is that at a junction, the sum of the current into it is equal to the sum of the current out of it. So for example, let's say there's a junction where there's a wire here and there's a wire there and there's a wire here and maybe there's a wire there. Any currents I have going in have to be equal to the sum of the currents I have going out. So in this case, this means I1 plus I2 would be equal to I3 plus I4. This is the rule that we've been using to talk about what it means for for elements to be in series. It means the current going in is equal to the current going out. Here, we're just applying that to a junction where things are split, potentially split in lots of different ways. It doesn't really matter. Now, one thing to be aware of is sometimes we don't know what's going on. For example, let's look at our circuit up here. Do we know the direction of the current? It might be tempting to say that here the conventional current goes this way because this is the side of our positive terminal. And here the conventional current presumably goes this way because this is the positive side of this terminal. But what's going on over here? Is it going that way? Let's try that. Maybe it's going this way. But then what's going on over here? If the current is going this way, we might think, okay, well, it's going to be split. It's going to go this way and then split that way. So that might tell us that it's going to be moving in this direction. On the other hand, if we think about what's going on with the current that we drew over here due to this battery, right, this current is going this way, so we might say it's going to be split this way, that way, and this way. And so that would imply that we've got some current going this way. Well, the current can't be pointing counterclockwise and clockwise in this segment of our loop at the same time. It's one or the other. In other words, one of these batteries is going to beat out the other battery. And that will depend on which battery is stronger and what's going on with these resistors. And so the details are hard to predict. We might not actually know. So in order to actually deal with the junction rule, sometimes when we calculate the currents in and the currents out, we don't know which ones are going in and which ones are going out. For example, let's look at this junction. If the current from here, let's call this I1, well, that's probably going into this, or at least using the direction that we've chosen here, that's going to be going into this junction at the bottom. On the other hand, we have these two other currents. Let's call the current through this middle section I2 and through this third section I3. But I don't know whether I'm assuming that I2 is probably going out that way. That seems reasonable, but you never know. I could be wrong. So that's probably outgoing. And we're guessing that this is probably ingoing. But we don't know whether this is going in or out. And so it's not really a good way of representing what's going on because I don't know which side to put which of these currents on. So a clearer way of representing this is that the total current entering a junction is equal to 0. And all that says is that, well, the total current is 0, which means just as much is positive as is negative, just as much is entering as is leaving. This way I can simply write I1 plus I2 plus I3 plus I4 equals 0. And if I put in some of these as positive, for example, if I know I1, if I plug in a number for this, maybe I've calculated it or already, or I know, or I've measured it, or I've been given what this value is. If I plug some of these in, it will allow me to figure out what's going on with the others. And if I find, for example, that I3 is negative, that means it's going to be leaving in the convention that I picked. If I found that I3 is positive, it would mean that it's entering in the convention that I picked. And so some of this depends on your choice and how you define to choose variables. But this is, I think, a cleaner way of representing the junction rule as just the sum of all current entering a circuit is 0, and negative current means it's leaving rather than entering. That way the math will just tell you what's going on. The loop rule is a bit more complicated, but on the other hand, it's where most of the magic actually happens. It's what allows us to really figure out what's going on, although we do actually need both of them. So here's what we're going to do. The loop rule is really nothing other than a statement of conservation of energy, just like the junction rule is really a statement of conservation of charge. So for the loop rule, what it tells us is that the sum of the potential differences around any closed loop must be 0. In other words, the sum of V around a loop is equal to 0. And all that's saying is, if I start right here, if I go all the way around this loop and end where I started at, I have to have the same final value of potential that I started with. And since the change in potential or the voltage from point A to point B is simply the difference in potential at point A, or from point A to point B, well, if my initial and final position are the same, then my initial and final potential are the same, and so I have to have arrived at the same value. There must be a voltage of 0 around any closed loop. If that were not the case, then current going around and around and around would generate basically infinite amount of energy. Each time our current circulates, it just builds up more and more and more and more energy, and that's not really what happens in the circuit. The battery can continue to provide energy, but what that would mean if the potential difference were literally a different value, two different values at one point, then I can bring a charge from here through some path back to here, but have more energy than I started with, even though I did a total of 0 work because I moved it along a closed path. And electric fields are conservative fields, and so that doesn't work. It would violate conservation of energy. And so the loop rule allows me to add up my potential differences across each part of my circuit. Now there are a couple ground rules, and that's as follows. When tracing a loop in the same direction as the current, V across resistors is negative. That's because the potential goes down across a resistor if you're going in the direction of current, because we're going in the direction that positive charges are moving, and positive charges move from high potential to low potential. Or maybe here's a better example, from high potential to low potential towards the negative terminal. And so if you're going around in the same direction that your current is going, then every time you cross a resistor, you subtract the voltage across the resistor. And that's what we often call this a voltage drop. Meanwhile, V across a battery is positive. And that's just because the battery provides potential difference. So if I go from the negative terminal to the positive terminal, I'm going to increase my voltage. I should say, so you can always figure out the voltage across a battery, whether it's positive or negative, simply by, are you going from the bottom, from the negative to the positive terminal, or are you going from the positive to the negative terminal? Because in the end, I can trace a loop either way I go, and whether it's my resistors that are decreasing potential or my battery simply depends on the direction that I chose to trace out my loop. It doesn't actually matter which way you go. So let's actually work this out for our little circuit here. I'm just going to scroll up so we have some room. So let's start by writing down our junction rule equations. So we have two junctions, one at the top and one at the bottom. Now let's use the blue directions. So let's assume that the current is going the way I've drawn them here. If we made a mistake, if the current is actually going to the right here instead of down here, we'll get a negative answer, a negative number somewhere for one of our results, and that will simply tell us we picked wrong. And so we just reverse it. So the math will actually let us know if we guessed incorrectly. So the top one tells us that, so I know that the total current entering that has to be equal to 0. And I have written that I2 is entering. Meanwhile, I've written that I1 is leaving because I1 is going this way, and that I3 is also leaving. And so this tells me, where I've put in magnitudes of here, that this is the equation relating our currents together through the top. Now I can also write a second equation for the bottom, but you'll actually find in this case it's redundant because I have I1 plus I3 minus I2. And that's just the negation of this whole thing. It's just moving everything to the other side. So in this case, the junction rule only gives me one equation to use. So that's not enough. I've got all kinds of things in here. Even if I know V1, V2, R1, R2, and R3, I don't know what V1 is. I don't know. This is bad notation. We'll fix that later. I don't know what the voltage across R1 is, and I don't know what the voltage across R2 is or R3. I don't know what the values of the currents are, so there's so many unknowns here. Now, bear in mind that when we're dealing with circuits, we actually have a ton of equations because we actually have V equals IR, and we have this for every single one of our resistors. So that immediately gives us 3 equations to use. So in order to fix my notation problem, I'm going to change the voltages of my battery, and I'm going to use the symbol for EMF, electromotive force, which is another common way of representing the potential difference supplied by a battery. So this will just allow us to distinguish between the voltage across resistor 1 and the EMF or voltage of battery 1. Now let's look at the equations we can write from the loop rule. Well, first of all, how many different loops are there? There are actually 3. There's the outer loop, there's the left loop, and there's the right loop. And in each one of these loops, I can choose to go whichever way I want. Typically, it's easiest to go around a loop in the direction that the current is flowing. So for this left one, I would go this way. For this right one, I would go this way. But if you look at the outer loop, there is no direction I can pick where I'll always be going in the direction of my current. If I go counterclockwise, then on the right hand here, on the right side, I'm going the wrong way. But if I go clockwise, then I'm going the wrong way on the left side. So I just have to pick one, and it doesn't really matter. So we're not going to need all of these loops, but let's just write down the equations we would get for each of them anyway. So for the left loop, I'm going to choose to go in the direction of the currents. So I'm going to go counterclockwise. So I'm going to start by adding the EMF of the battery. Then nothing changes along here. Then as I cross R2, I'm going in the direction that I've labeled my current. So I would expect to lose potential. Then I'm going across the second battery from low to high. So I would add that back, and then I lose more potential across resistor 1. And I know that all of that has to add up to 0. On the right-hand side, I can do the same thing. I'm going to start just before battery 2. I like to start by battery, but you don't have to. So I'm going to go in the direction where this is going to give me a positive potential difference across my battery. So I'm starting at the negative terminal, and I add EMF2. Then I lose potential as I go across resistor 3, because I'm going in the direction of our positive current. And then I'm going to lose more potential as I cross resistor 2. And then I return to where I started, and so the total potential difference has to be 0. And lastly, I can write out our outer loop. Let's write it over here. And our outer loop, let's start by EMF 1 again. So I'm going to go in the counterclockwise direction, and that's going to add EMF 1. Then the next time I get to here, I'm crossing R3, but you'll notice I'm going the wrong way. I said that my current is going this way, and I'm crossing this way. So I'm actually going from the low side, the low potential side, to the high potential side. And so that means I need to add V3. And then I continue this way, and now I'm going in the correct direction with my current, and so I subtract V1, and that gives me 0. And so I have a whole ton of equations. I have 3 Ohm's laws. I have my junction rule, and I have each of my loop rules. So the junction and the loop rules by themselves, you can't really put them together. One is about voltage, one is about current, and that's where Ohm's law comes in. I can rewrite, for example, each of my loop rules in terms of current and resistances. So V2 is simply equal to I2 times R2, and this is epsilon, E2, and this is minus I1 times R1 equals 0. And I can do the same thing over here. So this is EMF2 minus I3 R3 minus I2 R2 equals 0. And I can do the same thing over here for my outer one, EMF1 plus I3 R3 minus I1 R1 is equal to 0. And you'll notice, assuming I started with all the values of the batteries and the resistors, well, there's only 3 unknowns anymore. There's I2, there's I1, there's I3, here's I2 again, here's I3 again, here's I1 again, and they're also represented up here. The currents are the only things I don't know. And that's only 3 things I don't know. So I don't need all of these equations. Typically what happens is you are going to require you're going to need your junction rule equation, at least for a small enough circuit like this. And you're going to need any 2, usually, of your loops. Sometimes one of the loops won't really give you very much information. Sometimes a certain combination of 2 of them might not actually give you enough information. You need to pick the other. There's a little bit of an art to this. We'll go over some better ways of solving these kinds of systems of equations later. But the key here is, at this point, we just want to solve this system of equations. So let's try to work through this. I don't really need my circuit diagram anymore. I just need my equations. Let's try to identify a set of equations that will be kind of easy. So Note that in each of my loop rules, I have 2 of my currents. Now, if I can find 2 of these that have the same 2 currents in them, I might be able to solve for them and then use another equation to figure that out. But unfortunately, I can't. Here I have I2, I3, I1, I2, I1, I3. So that's not going to help. But I can pick any 2 of these. And I'm going to avoid the one on the left because it's the messiest. So I'm going to pick the 2 on the right. And I can solve for one of these in terms of the other. So for example, on the right, on these 2 that I'm going to pick, they both have I3 in common. So I'm going to get rid of I3. I'm going to isolate I3 and I'm going to solve for I1 in terms of I2. And so let's isolate I3 in the right loop. And so that gives me I3. Oops, I don't want that color. Let's do it over here. I3 is going to be equal to EMF2 minus I2 times R2 divided by R3. I can then plug that in to my outer loop, and that gives me, so this is from the right loop. I can plug this into my outer loop, and that gives me EMF1 plus EMF2 minus I2 R2 over R3 minus I1 R1, and that's equal to 0. And this lets me solve for R1 in terms of I2, and that gives me R1 is equal to EMF1 over I1 plus EMF2 minus I2 times R2 over I1 times R3. So, oops, I'm sorry. This is supposed to be I1, and this is supposed to be R1. Oops, and this is also supposed to be R1. Now what I can do is, this is I1 in terms of I2. I can take that and I can plug that into here. I1 and I2 I can write as a single thing. I can then solve for I1 or I2 in terms of I3. And then I can plug back into here and I can arrive at my final answer. I'm not going to do all that algebra here. I guarantee you I'm going to screw it up if I do it right now. But this is the process. This is how you go about solving things. I will be uploading a video in the next day or so going over some examples. I think this is a terrible way to actually approach these problems. As you can see, the algebra quickly becomes a bit of a nightmare. And if you're at all like me, there's no way you're ever going to get the right answer through this. So I'm going to go over some methods of what you can do to solve these kinds of problems more easily. You can use your calculators. Unfortunately, I don't actually know how to do this on your calculators because I have not used one of those since I was your age. About the time of the Spanish flu, probably. But I'll show you a different way using matrices, and I'm going to look for instructions for how to actually solve these kinds of systems of equations on your calculator as well. Now, in the meantime, before I leave it here, another thing that or something else I want to point out is that this kind of process allows you to solve really complicated problems in surprisingly easy ways. So some of your homework questions involve circuits that look really, 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 really crazy. In particular, I'm talking about the questions in chapter 26. Or is it, no, the questions in chapter 27. Not the problems, the question. Like tons of resistors and batteries everywhere. But the key is, if you can identify loops that are nice and simple, you can actually use the loop rule to very quickly arrive at results as long as you are able to keep your loops contained to almost entirely things that you already know. So that's a pretty big hint. I'm going to let you try to work out the rest. You do have a homework posted. The first part of the homework, or part of the homework, is on Albert, and it's on, for the most part, relatively simple circuits. So parallel series, simple complex circuits that you don't need all this fancy stuff for, as well as some of the other stuff like power. The second part of your homework that's due tomorrow on Tuesday is questions from the textbook. Again, a combination. Some of them are about drift velocity, just a little bit of review. And then some of them are more conceptual nature about these kinds of complicated circuits. There's an additional assignment posted at the same time that's due on Wednesday. That involves more detailed, more complicated, and quantitative analysis of these kinds of circuits. You're welcome if you have the time and motivation to get started on that now. You technically have the tools to actually do it. But if you get stuck or if you're busy, it's not the end of the world. I'll be posting another video of me working out some examples. And you can always talk to me during office hours as well. All right, everybody. I will see you next time.